In this video, I will talk about complex numbers. Complex numbers will be extensively used in electric circuits, as we will see in the following chapters of this course. Complex numbers can be also used in so many applications in engineering and physics, like electromagnetism and classical mechanics. I should mention that we always use complex numbers in an auxiliary way. They are not directly relevant because we are always interested in analyzing real quantities. For example, the electric field is real, the position is real, the velocity is real, but the bottom line is we always use complex numbers in order to simplify the mathematical analysis in most scenarios. Let us go over the definition of the complex number. Okay, so a complex number is any number of the form z is equal to x plus jy, where x and y are real numbers. X is called the real part of the complex number z and is denoted by real of z. And y is called the imaginary part of z and is denoted by the imaginary of z. I should mention that the imaginary part of z is not jy. The imaginary part of z is only y. Here, j is equal to square root of minus 1. J was invented by mathematicians in order to solve equations like x squared is equal to minus 1. And it just so happens that by inventing j, we do not need to invent more numbers because we can solve every polynomial equation with just j. Okay. Anyway, it follows immediately from this result that j squared is equal to minus 1. And of course, j to the power 3 is equivalent to j to the power 2 multiplied by j, which is again minus 1 multiplied by j, which is minus j. Now, j to the power 4 can be expressed as j to the power 2 multiplied by itself, which is again minus 1 times minus 1, which is 1. In general, j to the power n plus 4 is equivalent to j to the power n multiplied by j to the power 4. And since j to the power 4 is equal to 1, then we can again write j to the power n plus 4 equals j to the power n. Now, if we have been asked to obtain j to the power minus 1, then one can write j to the power minus 1 as j to the power minus 1 plus 4, which is again j to the power 3, which is again minus j, as we can see in this equation. Okay, I should mention here that if the imaginary part y of a complex number is 0, then the complex number will reduce to a real number. In fact, we can say that every real number is a complex number with 0 imaginary part. But the converse is not true, of course. Often it's useful to think about or think of a complex number z x plus jy as a vector in a two-dimensional space, as we can see in this pictorial representation. So here we have this point is 0, 0, and this point can be represented by x, comma, jy. And this vector or this complex number can be expressed as z is equivalent to x plus jy. Now, this is known by the Cartesian form, okay? So this is known as the Cartesian form. Z is equivalent to x plus jy. Just like we treat vectors, we can treat this complex numbers in the same way. So in that sense, we can say that this complex number has a length of r and an angle theta that is measured from the positive x-axis, where r and theta can be, of course, expressed in terms of x and y. So it turns out from this graphical representation that r is, or that x is equivalent to r cosine theta, and y is equivalent to r sine theta. So we can express z x plus jy as we can see here So Z is equivalent to R cosine theta plus J R sine theta. So where R is called the magnitude of Z, this is called the magnitude of the complex number Z, and theta is called the phase of the complex number Z. So the magnitude of Z is just denoted by absolute value of Z, as we can see here, and theta, we can say that theta is the argument of Z, or just angle Z. Now, it turns out from Euler's identities that we can express this complex number, R cosine theta plus J R sine theta, in terms of R multiplied by complex exponential. So R cosine theta plus J R sine theta is equivalent to R e to the power j theta, which can be also expressed as R angle theta. Okay? Now, in fact, it's non-trivial to show that this form or this representation is equivalent to R e to the power j theta. You have to work a bit in order to show that this equality holds. But the bottom line is, let us accept it as it is in our context, okay? We will not discuss the proof of this result. Anyway, it turns out from the representation in equation 3 that this form is known as the polar or the exponential form. So Z is equivalent to R cosine theta plus J R sine theta, which is equivalent to R e to the power j theta, and this is known as the polar form. Now, one can convert a complex number from Cartesian form to exponential or polar form, and vice versa. So, and this is easy now if we put together the relationships or between x, y, r, and theta, then we end up with having the following. So x is equivalent to R cosine theta and y is equivalent to R sine theta. And of course, if we are given R and theta, we can obtain x and y, and then we can convert a complex number from the exponential form to the Cartesian form. And again, if we are given the Cartesian form, then it turns out from these two relations that we can say that R is equivalent to the square root of x squared plus y squared, and theta is nothing but tan inverse y over x. And in that sense, if we are given x and y, we can obtain R and theta. Now, one can observe from equation 3, as we can see here, that e to the power j pi can be expressed as we can see here. So e to the power j pi is equivalent to 1 e to the power j pi. So remember, R e to the power j theta is equivalent to R cosine theta plus j R sine theta. So here we have R is equal to 1 and theta is equal to pi. So e to the power j pi is nothing but cosine pi plus j sine pi, which is again is equivalent to -1 because cosine pi is -1 and sine pi is 0. So this part will be 0. So we end up with having this interesting relationship. E to the power j pi is equivalent to -1. By the way, this is known as the queen of all equations. E to the power j pi plus 0 plus 1 is equal to 0. Now, it turns out also from the exponential form that e to the power j pi over 2 is cosine pi over 2 plus j sine pi over 2. And since cosine pi over 2 is 0, then we end up with having e to the power j pi over 2 is equivalent to j sine pi over 2, which is 1. So, and this is nothing but j. And again, e to the power minus j pi over 2, one can show that this will be equivalent to -j. One important result is that e to the power j 2 pi is equivalent to cosine 2 pi plus j sine 2 pi. And again, sine 2 pi is equal to 0 and cosine 2 pi is equal to 1. So we infer that e to the power j 2 pi is equivalent to 1. In fact, this result can be generalized So for any integer k, so we have e to the power j 2 pi k is equivalent to cosine 2 pi k plus j sine 2 pi k. And since sine 2 pi k is equal to 0, then we end up with having e to the power j 2 pi k is equivalent to cosine 2 pi k. For integer k, cosine 2 pi k is always 1. So for integer k, we can say that e to the power j 2 pi k is equivalent to 1. Now, in view of this result, one can observe that adding 2 pi to the angle does not change the complex number. In fact, one can write r e to the power j theta is equal to r e to the power j theta plus 2 pi k, since e to the power j 2 pi k is equal to 1. Okay? Now, let us consider the definition of the complex conjugate. The conjugate of a complex number z, x plus jy, is given by z star, or z conjugate, is equal to x minus jy. We just replaced j with minus j. Now, if the complex number z is expressed in the exponential form, as z is equivalent to r e to the power j theta, then the complex conjugate, z conjugate, is given by r e to the power minus j theta. As I just said, in general, to find the conjugate of a complex number, we have to replace every j with minus j. As we can see here from this figure, so if this is the complex number z, x plus jy, then the complex conjugate of this complex number, z conjugate, x minus jy, as we can see here. We have to replace every j with minus j. Now we will consider some operations on complex numbers. So basically, if we have a complex number z, where z is equal to x plus jy, which can, of course, be represented in terms of the complex exponential form, r e to the power j theta. Similarly, we have z1 is equivalent to x1 plus jy1, and is equal to r1 e to the power j theta 1. z2 is equal to x2 plus jy2, and it is equal to r2 e to the power j theta 2. Then one might be interested in obtaining the sum z1 plus z2. So as we can see, in order to find this sum, we have to add the real parts together and the imaginary parts together. So z1 plus z2 is equivalent to x1 plus x2 plus j y1 plus y2. Similarly, if we want to find z1 minus z2, then one has to say that this should be equivalent to x1 minus x2 plus j y1 minus y2. Now, if we are given z1 and z2 in their polar form only, and if we have been asked to find z1 plus z2, then maybe the only way we can do it is to convert z1 and z2 into the Cartesian form, and then we can add them as we just saw here. Now, what about z1 times z2? So z1 times z2 is x1 plus jy1 multiplied by x2 plus jy2. And if you expand this product, so we end up with having x1, x2 minus y1, y2 plus j x1, y2 plus x2, y1. And this product is being performed in the Cartesian form. Now, if we have z1 and z2 in the polar form, then one might write z1 multiplied by z2 is r1 e to the power j theta 1 multiplied by r2 e to the power j theta 2, which is simply r1 r2 e to the power j theta 1 plus theta 2. Now we have an interesting property here. If we multiply the complex number z by its conjugate, z conjugate, then the result is real, okay? And this should be equivalent to r square, where r square is equivalent to x square plus y square. Okay, so z conjugate is equivalent to x plus jy multiplied by x minus jy. So this is x square plus or minus jxy plus jxy plus jy multiplied by minus jy, which is y squared. So we end up with having x squared plus y squared, which is nothing but r squared, by the way, where r is the magnitude of the vector z, of the complex number z. Now, look at this one here. We have z times z conjugate is equivalent to r squared. So r, which is the magnitude of z, of course, should be equivalent to the square root of z conjugate, or z conjugate z is the same. Now, if we are given z1 and z2, and we have been asked to find z1 divided by z2, then one way to write this is to do the following. So x1 plus jy1 divided by x2 plus jy2. And here the main challenge is to write this expression in terms of real quantity plus j imaginary. Okay, and this can be done basically by multiplying by the conjugate of this quantity. So as we can see, x1 plus jy1 divided by x2 plus jy2 is equivalent to itself multiplied by x2 minus jy2 divided by x2 minus jy2. So here nothing has been changed. This quantity is 1 basically. So I multiply this quantity by 1. That's it. Okay. Now I will take advantage of the conjugate property. So x2 plus jy2 multiplied by x2 minus jy2, it should give us x2 squared plus y2 squared. And if you expand this product, x1 plus jy1 multiplied by x2 minus jy2, after some simplification, we can obtain or we can simplify z1 divided by z2 as we can see here. It's a real quantity plus j imaginary quantity. Now, or imaginary part. Okay, so now here we have, if we are given z1 and z2 in the polar form, then we can find z1 divided by z2 easily by having r1 e to the power j theta 1 divided by r2 e to the power j theta 2, and then in that case we can write r1 divided by r2 e to the power j theta 1 minus theta 2. Now, based on the above operations, the following facts about complex numbers can be verified. z1 plus z2 over all conjugate is equivalent to z1 conjugate plus z2 conjugate. z1 z2 over all conjugate is equivalent to z1 conjugate multiplied by z2 conjugate. And z1 divided by z2 over all conjugate is z1 conjugate divided by z2 conjugate. Now, z1 minus z2, or the magnitude of z1 minus z2, it should be equivalent to this quantity. And here z1 minus z2, or the magnitude of z1 minus z2, is the square root of the distance between these two complex numbers, z1 and z2. z1 times z2 magnitude is equivalent to the magnitude of z1 multiplied by the magnitude of z2. And similarly, the magnitude of z1 divided by z2 is equivalent to the magnitude of z1 divided by the magnitude of z2. And we have two interesting properties here, as we can see. Real of z, which is equivalent, of course, to x, it can be expressed in terms of z and z conjugate. So real of z is 1/2 multiplied by z plus z conjugate, and the imaginary of z, which is y, is equivalent to 1/2j multiplied by z minus z conjugate. And these two relationships are valid for any complex number z. Now let us consider the following example. So if we have z1 8 plus 3j and z2 9 minus 2j, then it's obvious that real of z1 is equivalent to 8 and imaginary of z1 is equivalent to 3. Now, if you have been asked to find z1 plus z2, then we have to add the real parts together. So it's 9 plus 8, 17, and the imaginary parts together. So it's 3j minus 2j, which is j. Similarly, we can proceed and find z1 times z2. So by multiplying these two complex numbers, as we can see here. So after some simplification, we end up with having the following result. Now, for z1 divided by z2, we have to multiply by the conjugate of 9 minus 2j. And then after some simplification, we end up with having this result. So Z1 divided by Z2 is equivalent to 66 divided by 85 plus J 43 divided by 85. Now, in this example, we would like to express Z1 and Z2 in the polar and the exponential form. So if Z1 is equivalent to 6 plus J8, then the complex number Z1 lies in the first quadrant. And one can easily find R1, which is the square root of x plus x squared plus y squared. Now, it turns out that R1 is equivalent to 10. Now, in order to find theta 1, theta is tan inverse y over x. And since this complex number lies in the first quadrant, then we infer that theta is equivalent to tan inverse 8 over 6, which is 53, almost 53 degrees. Okay? Then we can write the complex number z in the polar form and in the complex exponential form. Now, for Z2, 6 minus J8, of course, it will have the same magnitude as we can see here. Here, the only thing that is different is that we have to find the angle theta. And one can observe that Z2, or this complex number, lies in the fourth quadrant, and therefore we have to be very careful when we obtain theta, okay? Since this complex number lies in the fourth quadrant, then theta 2 can be obtained as we can see here. So it's 360 degrees minus tan inverse 8 over 6. So after simplification, one can obtain this value. So, and then finally, we have this vector or this complex number in terms of polar representation and the exponential representation or complex exponential representation.